light does an interesting thing when it passes from one medium to another. We know that the speed of light we've learned is c. However, light changes speeds when it's in different mediums. C is the speed of light in a vacuum, but light is slower in actual materials than it is in vacuum, and it's slower in some materials than in others. We're going to look at, and because it speeds up or slows down, that causes the light to bend. Now, it might not seem obvious that it would bend. It might just seem like it would keep going along the same line, but slower. But let's look at some geometry here. So this, if we say that we're at some point the light is here, and then at some later time it reaches the boundary between these two media. So this is medium 1, medium 2. In that time, it has traveled some distance, and that distance is whatever its speed was times time. Okay. Now if we extend this line over here, by similar triangles, this is also theta 1. And if we make another line that's perpendicular to this guy, and then we kind of draw in a line that's parallel to this guy, we can make another little triangle over here. And this distance, of course, that it's traveled in this time is v2 times time. So in the same amount of time it's traveled some distance, whatever. And we're not assuming that these are different as of yet, but that means that this too is v2 times time over here. Okay? And then just following trigonometry, this side is shared, okay? And this right here is a right angle. So this side of the two is shared, and by similar triangles, this, again, is theta 2, because this is a right angle, which means that this is the complement of theta 2, which means that this is theta 2 again. So if we look at our triangles that we've made, the sine of theta 2 is equal to v2t over, whatever that thing is. Meanwhile, the sine of theta 1 is equal to v1t over, again, that whatever that side is, x, which means if we divide these two, sine theta 1 over sine theta 2, we've got a v1t over x over v2t over x, so our x's and t's cancel out. And we've got that sine theta 1 over sine theta 2 is equal to v1 over v2. And so, this just mathematically shows that if a speed changes, then this angle is also going to change. Now, in general, the speed of light in a material is equal to the speed of light over n, where n is known as the index of refraction of the material. Okay, and the index of refraction is a property of whatever the material is. On page 922, there's a table that has all the indices of refraction of various substances, and you'll use those in your homework problem. So looking at this relationship, V1 would be C over N1, V2 would be C over N2, and plugging those in would give us sine theta 1 over sine theta 2 is equal to C over N1 over C over N2, which is just N2 over N1. And then we cross multiply and get N1 sine theta 1 equals N2 sine theta 2. This is called Snell's law, because a guy named Snell came up with it, I guess. And that is the equation that is very important for refraction. Right? And we can, again, as usual, when we get these equations, we can, given these various values, we can calculate any of the other values in the equation. Now let's look at our equation to do some qualitative stuff. Now, going back a step, we had this. Okay. So let's see what happens here. If n2 is greater than n1, that means that sine theta 1 is greater than sine theta 2. Okay? So that means that if we go from a lower index of refraction to a higher index of refraction, we get a smaller sine in our first material. Now, we're only dealing with acute angles, so that means that our angles are also, one is bigger than the other, because sine is increasing from 0 to 90. Right? So sine is its maximum at 90 or pi over 2, and a minimum at 0, and between those two it's increasing the whole way. So this means that as we go from a lower index of refraction to higher, then the light rays will bend toward the normal and vice versa. Okay. So if we go from a lower index of refraction to higher, the light rays will bend toward the normal. If we go from a higher index of refraction to lower, the light rays will bend away from the normal. Right? Let's take a look at a particular example that'll help us work out some stuff related to refraction. Okay, so here's our question. You're standing on a dock. Sorry, that looks kind of like clock. That's a D. Pretend they're connected. You're sitting at a dock so that your eyes are 2 meters above the water. You see an object on the floor of this clear lake as you look at an angle of 75 degrees below the horizontal. And the question is, how far from the dock is the object located? Now, if there wasn't water involved, and the bottom of the, I didn't write it down, but I'm going to say that the lake is 5 meters deep at the point where you're looking. Now, if there wasn't the lake involved, this would just be a simple trigonometry problem. You'd have the angle, and you'd know what the height was. The total height is 7 meters, and so you could use trig to calculate, that horizontal distance, and the horizontal distance is what we're looking for. But this is a little bit more complicated, because we're not going along this straight line path. The object is actually going to be closer to you than the straight line path would indicate, because, whatever this object is, the light ray will go up here, and water has an index of refraction of 1.33. It would probably serve you well to know that the index of refraction of water is 1.33. Index of refraction of air is 1.0003. Mostly we'll just use 1. Light doesn't slow down very much in air. And so we know that the angle to the normal is going to be smaller in water than it is in the air. So we can say that's our theta 1, that's our theta 2. And we can figure out what those angles are, and once we do that, we can figure out how far from the dock. This is what we want to know. That distance will be the answer to our question. So, got a couple pieces to figure out. Well, first off, our theta 2 is the complement of 75, 15 degrees. Then we can use Snell's law to figure out theta 1. We know N1, which I've said water is 1. N1 sine theta 1 equals N2 sine theta 2. And so we can figure out what that angle is for water. Just go sine 15 divided by, am I in degree mode? Yes, 1.33, inverse sine of the answer, and we get that our theta 1 is 11.22 and so forth degrees. I'll store that as A. Store that in my calculator. And now, from there, we're just doing a little bit of trig. So up here we have a triangle. We know that this side of the triangle is 2 meters, this is 75, and so this horizontal distance, to the point where the light rays are emerging from the water, we can just say that the tangent of 75 is equal to the 2 meters over that first horizontal distance. Tangent 75 equals 2 over x1. So that distance is 2 over tan 75, which is 0.535, etc., which I'll store. And then this second distance, which I'll call x2, we can just say that that's 5 degrees. We can say that the tangent of theta 1 is equal to opposite over hypotenuse, that's x2 over 5. So I can take the tangent of this 11.22 whatever and multiply by 5 and get that x2 is 0.99, etc. And I'll just add that together. x1 plus x2 is our distance, which then I get is 1.5278, or about 1.5 meters, which tells you my drawing is clearly not to scale. This is like a 45-degree angle, and I call it 75. But anyway, so that's a neat little problem that we can do, solve using refraction. Refraction is also responsible for the production of mirages in the desert. So what basically happens is that the air near the ground is hot and therefore less dense than there's cooler air up higher. And so the less dense air has a smaller index of refraction than the hotter air. And because so there's light coming from, say the top of a tree or a cactus or whatever, and it's moving downward toward the ground. But because it's heading into less dense air with a lower index of refraction, it starts bending away from the normal, and it kind of does that rather than there is no, obviously there is no set divide between this hotter and colder air. It's all kind of a continuous thing, and so it starts curving, and then by the time it gets to our eyes, it's actually curved upward, and so it appears that we're seeing something, at some angle. And, maybe it's further out, but it appears that we're seeing something here when it's actually, up over here. So in a desert, the mirage of water is actually the blue light from the sky then being bent this way and getting to your eyes. And so you see the sky and you think, hey, look, there's water, because if you see something blue on the ground, you think it's water. So that's how mirages occur.